Newton's third law says that forces come in pairs, sometimes called action-reaction pairs. When an object A exerts a force on some other object B reacts by exerting a force of equal magnitude but opposite direction on A. So in this example, object A is a person of mass 70 kilograms. Object B might be a block of wood or whatever. Its mass is 300 kilograms. Now in this example we will be dealing with a contact force. Okay, object A applies a force on object B by pushing on object B. It's important to realize, however, that Newton's third law applies to any type of force. The objects exerting the forces don't have to be in contact with each other. For example, one of the objects might just be a single electron. The other object might be a collection of many electrons. So this object is not in contact with this object over here. So this second object, which we call B, is a collection of electrons. It's a fact that the force exerted on this electron, this single electron, due to this collection of electrons, has the same magnitude as the force on the collection of electrons due to just this single electron. Okay, the forces will have the same magnitude but be opposite in direction. As a matter of fact, if this is a collection of electrons, the force on this collection due to this single electron will be repulsive. It will be in this direction, in a direction away from this electron. Okay, something like this. But Newton's third law says the force on this single electron will be in this direction. It will have the same magnitude as this vector but point in the opposite direction. Okay, let's get back to this problem. The force that object A exerts on object B can be written FBA. So it's the force on B due to A. Now, in other places you might see this written the other way around. You might see it written as FAB, the force on A due to B. Okay, now I prefer to use this notation. So the first letter is the object that the force is exerted on. The second letter in the subscript is the object that is exerting the force, which is A. So we read this as the force on B due to A. Let that magnitude be 10 newtons to the right. It's a horizontal force, no vertical component. By the way, 10 newtons is equivalent to the weight of a bag of sugar. A standard bag of sugar has a mass of 1 kilogram. So the weight would be mg, which is 1 times 9.81. So 9.81 newtons is the weight of a bag of sugar, which is close to the kind of force we're dealing with here. Now let's get the force on A due to B. By Newton's third law, that's equal in magnitude but opposite in direction. So I'm trying to draw a vector of the same length as this vector here. Its magnitude is 10 newtons. But it's a different vector. We can call it the force on A due to B. We can summarize Newton's third law by this vector equation. This vector equation tells us two things. The first thing it tells us is that vector FAB is pointing in a direction that's opposite to vector FBA. Now we saw that in the section on vectors. If we stick a minus sign in front of a vector, so we stick a minus sign in front of this vector here, FBA, we reverse its direction. Now the second thing that this equation tells us is that the magnitudes of these two vectors are the same. Let's see that by getting the magnitude of this vector here. Well, we have a minus 1 times this vector. Okay, when we stick a minus sign in front of a vector, it's equivalent to multiplying by the scalar minus 1. Now the magnitude of a product of quantities is actually the same as the product of the magnitudes. The magnitude of minus 1 is plus 1, and the magnitude of vector FBA can be written FBA without an arrow. So we just get FBA, and we know that that's 10 newtons. But that's the same as FAB, the magnitude of vector FAB. So this equation here essentially sums up Newton's third law. It doesn't matter what the objects A and B are. It doesn't matter if the force between them is a contact force. These objects could be some distance apart. We could be dealing with an electrical force between the two objects. We could be dealing with a gravitational force between the two objects. It doesn't matter what the nature of the force is. Now, this result is not as intuitive as it seems. Let's consider the case of a car colliding with a large truck. We can imagine a fairly small car involved in this collision, or even just someone on a bicycle involved in this collision. Let this vector here represent the force on the car due to the truck. So C for car, T for truck. Now, surprisingly, many people, including physics students, think that the magnitude of the force on the truck due to the car must be less than the magnitude of force on the car due to the truck. So they imagine that the force on the truck due to the car has smaller magnitude. But it's not true. Newton's third law says that these two vectors have the same magnitude. Okay, so you must draw vectors of equal magnitude but opposite direction. And it doesn't matter how small the car is. The mass of the truck could be 1,000 times greater than the mass of the object that the truck collides into. Yet these two forces have the same magnitude. Now, let's just go and get the acceleration of both of these objects. Now, I've set both of these objects on ice, so there are no other horizontal forces acting on these two objects. Okay, so the only horizontal forces acting on each of these objects is the mutual force, okay, the mutual contact force, which has a magnitude of 10 newtons. Okay, so we're assuming that the surfaces are perfectly smooth. Well, in reality, they're not perfectly smooth, but ice is pretty close. If the surfaces weren't smooth, then we would have another force acting on B in a direction opposing its motion, and similarly we would have another force on A in a direction opposing A's motion. These forces are called friction forces. So we are assuming that the only forces acting on these objects in the horizontal direction are the 10 Newton forces. Of course, we have the weights of the objects, but the weights have no component in the horizontal direction, so we can forget about them. So the weights contribute nothing to the acceleration of the objects in the horizontal direction. As a matter of fact, in the vertical direction, the force is zero, because if we take the weight of object B, it's cancelled by an equal and opposite force. Okay, because the object B does not accelerate in the vertical direction. The same is true for object A. So these two forces will cancel out for object B, so we can forget about them. So the resultant force on object B is a 10 Newton force to the right. And as I've said already, there's no friction force opposing that motion. Similarly, the resultant force on object A is a 10 Newton force to the left. So we can apply Newton's second law. The resultant force on object A has a magnitude of 10 newtons to the left, so the acceleration of object A is in the same direction as that resultant force. Okay, so we have to divide 10 by the mass of object A. Now the mass of object A is 70, so we get 1/7 meters per second squared to the left. Similarly, the resultant force on B is FBA. Its magnitude is 10. So by Newton's second law, that's the mass of B times the acceleration of B. Newton's second law tells us as well that the resultant force and the acceleration are in the same direction. So to get the acceleration, we divide the resultant force, which is 10, by the mass, which is 300. So we get 1/30th of a meter per second squared. So we see that object B will accelerate to the right with a smaller acceleration than object A. Object A accelerates to the left with an acceleration of 1/7. Finally, I just might mention something about the terms action-reaction. We could say that in this pair of forces, the action is FBA, the force exerted on B by person A. After all, B doesn't exert any. B is not the agent in this situation. A exerts the force on B, so we could refer to this as the action. And by Newton's third law then, B exerts an equal but opposite force on A, so this would be our reaction. Now it doesn't actually matter to the solution of the problem which force we call the action and which force we call the reaction. We could interchange these two terms and it won't make any difference to the solution of the problem. So in general we can forget about these. The terms action, reaction makes even less sense if we consider the gravitational force on an apple that's hanging from a tree. Okay, so we're considering the gravitational force due to the earth. That's just the weight of the apple. So if the apple's mass is little m, the weight is little m times g. If the apple was free to fall, it would accelerate with acceleration g, and Newton's second law, F equals ma, would give us this result here, with the acceleration equal to 9.81 meters per second squared. We could indicate this vector by FAE, the force on the apple due to the earth. Newton's third law tells us that there must be an equal and a force equal in magnitude but opposite in direction. Okay, the force on the earth due to the apple. I could show it like this here. So the magnitude of this force is mg, where m is the mass of the apple, and the magnitude of this force here must also be mg. Notice that it looks like things are not correct here. One would imagine that one of the forces will be much greater than the other force, but that's not the case. These forces have the same magnitude. Now which one is the action, which one is the reaction? Well, in this case it doesn't make any sense to talk about action-reaction pairs because which force was exerted first? Well, we can't really say that. Both forces are exerted simultaneously and they act over a distance. We are not dealing with a contact force here.